Okay, welcome to another video about maximum likelihood estimation. Today we're going to look at an example where we're trying to estimate two different parameters at the same time. So we have a normal model, and the two parameters are the mean and the standard deviation of the bell curve. We have some data. We have these n observations, x1 through xn, and these are fixed numbers. And so the likelihood function is this. And we did this example basically last time. The only thing that's different from last time is now we're also treating the sigma as an unknown parameter too. So the first thing I ask you to do is to find the log likelihood function, and all you do is you take the logarithm of everything in this expression, and then remember the rules of logarithms, so you can break up multiplication into an addition, and then because these are divided by 1, they're actually negative, and so you get this gets its own term, and you can pull down the power. That gets its own term, and then these guys inside the exponential function just are broken out of the exponential function like that. So this is the log likelihood function. The next thing I asked you to do is to find the partial derivatives of the log likelihood function, and that's not too hard to do. The partial derivatives with respect to mu, only these terms at the end here have mu. So you do the chain rule, you bring down the power, and then you multiply by the derivative of the inside, which is -1, so that makes them all positive. And so there you go, and the power 2 cancels with the 2 in the denominator. So this is the partial derivative of the log likelihood with respect to mu. And then the partial derivative with respect to sigma is similar. This time you need this term here, that matters because it has a sigma. So the derivative of this would be -n over sigma, so that's what I've got there. And then you do the derivative of each one of these with respect to sigma. That's a sigma to the -2 power, bring down the -2, and it makes it positive. The 2's cancel, and then you have a -3 power, so I just left that as sigma cubed on the bottom. The x minus mu quantity squared doesn't change because we're taking the derivative with respect to sigma. Okay, those are the two partial derivatives, and if you want to find the maximum likelihood estimator for both mu and for sigma, then you need to set these two partial derivatives equal to 0 so we can get to the top of the hill, right? This likelihood function is a function of two variables, and so we need to sort of get to the place where we're at the flat top of the hill where both directions have 0 partial derivative. Okay, so I set that equal to 0 in the next problem. And I give you this hint here in the next problem that if you want to find the critical point, the easiest thing to do is to first solve for mu using the simpler of the two partial derivatives. So looking at these two partial derivatives, this one is a little bit more complicated because it's got an extra term and some squares. This one's a little simpler. And so let's focus on the simpler one first and see if we can figure out what mu is. So we're going to set this equal to 0, and what I did here is I set it equal to 0, so 0 equals that partial derivative, and then I just factor out the common factor of 1 over sigma squared, and then what's left behind is a whole bunch of x's added up, and then a whole bunch of negative mu's. There's n copies of that. So this stuff in parentheses has to be 0 because definitely this is not going to be 0. And so when is that equal to 0? Well, I guess it's equal to 0 when mu is this stuff added up divided by n. And that's the x bar. All right, so this works exactly the same way as what we did last time when we just estimated mu. Now that we've got the estimator for mu, we can use that as our first solution, and we can substitute it into the second equation. And so we go back to the second partial derivative, this one, and we're going to substitute in x bar for mu, and then we're going to solve this equation for sigma. All right, so we go down here. Here's that equation copied down with the x bar substituted in for mu, and now I set it equal to 0. One thing I could do is I can move this negative term over to the other side, which I do on the next line. And then how am I going to solve this? Well, I guess I should maybe multiply both sides by sigma cubed, and so then I'll have sigma squared times n, because the sigma on the bottom will cancel out one of the sigmas on the top. And I'm doing this all in my head, but here's what I get when I do that and divide both sides by n. You get this expression for the variance, and then since I wanted the standard deviation, just take the square root of both sides. All right, and I rewrote it a different way with summation notation. That is the maximum likelihood estimator for the standard deviation. Now, one thing you might notice here is that this is dividing by n, not by n minus 1. So the maximum likelihood estimator is actually not the estimator we usually use to estimate sigma, and there's a reason for that. This estimator may be maximum likelihood, but it actually isn't the best estimator. It's got a problem. It's actually biased, which means that if you use this estimator, you're going to, on average, come out with a number that's a little bit too small. It's actually smaller than what you really want. And so to get the right estimator, we actually end up dividing by a different number here, and we go with something that's not maximum likelihood, but it's optimal in a different way. It's what we call an unbiased estimator, so that the average outcome that we get from different samples comes out closer to the true value of the parameter on average. We'll talk more about unbiased estimators next week, but I just wanted to point out right now, maximum likelihood estimators aren't always the best estimators, but this is the maximum likelihood estimator here. Okay, now I've said it was the maximum likelihood, but I never actually showed that. I did give an extra challenge problem here to actually show that our solution was the maximum likelihood estimators for mu and for sigma. You actually have to double check that it really is a maximum, so you do the second derivative test for multivariable functions, and the way that works is you find the Hessian matrix, which is the matrix of all the second partial derivatives, and then you check to see that the eigenvalues of that matrix are both negative. If they're both negative, then you have a local maximum. In this case, the Hessian matrix ends up being a diagonal matrix, which means that eigenvalues are just the two entries on the main diagonal, this one, and then these off-diagonal entries end up being 0. So that makes it pretty easy to check. So here's the work for that. It was just a little tedious. It's not really hard. So if you gave it a try, hopefully it wasn't too bad, but here's how I did it. First of all, here's the two partial derivatives, the first partial derivatives to get started. I just copied them so it's convenient. And now I need to find the partial derivatives a second time. So if I have the partial derivative with respect to mu, then the second partial derivative with respect to mu would be the partial derivative of all of this stuff with respect to mu. And these are each linear functions of mu. The partial derivative is just take the derivative of mu, it's just -1 over sigma squared for each one of the terms. If you add all those up, you get negative n over sigma squared. So the first top left entry is done. Then to get the partial derivative that's mixed, you take the partial derivative with respect to mu, and then take another partial derivative, this time with respect to sigma, and that's not too hard to do either. That's just to bring down the -2 power. The new power is -3. And so it's just -2 over sigma cubed, and then all this stuff up here just sticks around, so we get a sum of xi's minus n mu. And so that's done. It doesn't matter whether we do it partial derivative with respect to mu first and then partial derivative with respect to sigma like I did it, or if I did it the other way around, take the partial derivative with respect to sigma first and then the partial derivative with respect to mu. The order of that doesn't matter. That's one of the big ideas in multivariable calculus. So this and this are the same, so I don't really need to recalculate it. Last thing to do is to take the partial derivative of this expression with respect to sigma, and I did that down here. Again, not too hard, just a little tedious. And then we can substitute in for mu, because we know our critical point for mu is when mu is x bar. So if I substitute that in, the off diagonal entries of the have mu's in them, but if you plug in x bar here and multiply it by n, then you get the same thing as the sum of the xi's. So that just goes away, it becomes 0. So the two off diagonal entries are just 0. And then down here I've substituted in x bar for mu. And then I have this expression that I notice, the sum of the squares of the differences between xi and x bar, this deviation squared, that's part of the formula for our estimator for sigma, right? We found our best guess estimator for sigma was this formula. And so that's the sum of the squares just divided by n. So I just make that observation that if I only had a dividing by n here, then I would have basically my sigma, sigma squared actually, because there's no square root. So I just do that. I divide by n and then balance it out by multiplying by n, so I didn't really change anything. And then, hey, what is that? That's n sigma squared. So I'm going to substitute that in for this expression. And then I notice that I've got n over sigma squared, and then the sigma squared on top cancels with 2 of the sigmas on bottom, so then I have 3n over sigma squared, and that simplifies to this. And like I said, a little tedious, but we're done now because, hey, there's our Hessian matrix. And no matter what sigma is, no matter what this formula works out to be, it's going to be a positive number when you square it. And so the whole thing here is 2 negative terms on the diagonal, 2 zeros on the off diagonal. So the eigenvalues of these two numbers, and they're both negative. So this really is a local maximum according to the second derivative test. All right, so we have found the maximum likelihood estimates for mu and for sigma, and there are these two formulas. Okay, that's it. As always, if you have any questions, let me know.